Dear students, today we shall derive the Clausius Clapeyron equation. This equation actually modification of Clapeyron equation for a specific system. And therefore, let us first see what is the Clapeyron equation is, and then we can derive Clausius Clapeyron equation. To derive Clausius Clapeyron equation, and this equation is applicable to phase transition in one component system. That is a pure component system in which the system changes from one phase to another phase. It is considered one component and two phase system. The phase transition that may include solid and liquid phase transition in which they are at equilibrium at the melting point. And the second phase transition we may consider is the liquid and vapor which at equilibrium at the boiling point. The third phase transition we may consider is solid to vapor. Solid to vapor at sublimation temperature. And for the substance, the system, in some cases there may be two solids in phase transition, that is solid 1 and solid 2. For example, sulfur exists in rhombic sulfur and monoclinic sulfur, and they may be at the transition state. These two solids will be at equilibrium. Okay, for the derivation, let us consider a system that changes from phase A to another phase B, maybe any phase transition at constant temperature and pressure. Let us consider A and B are in equilibrium. The Gibbs free energy per mole of the two phases may be given Ga and Gb, where Ga is the free energy of phase A and Gb is the free energy at phase B. At equilibrium, the Ga and Gb will be equal. Okay, that is the delta G, change in free energy. Delta G is Gb minus Ga is equal to 0. Therefore, if the temperature of the system is increased, now we are going to increase the temperature of the system. For example, let us increase the temperature from T to T plus dt. We are increasing the temperature to dt. The pressure therefore will change from P to P plus dP. That is, this is the change of pressure to maintain the equilibrium. In this case, the relationship between dt and dP is derived from thermodynamics. We can derive that. Let us derive that relationship. As the temperature increased, the free energy also increases as follows. And Ga, as temperature increased from Ta to T plus dt, here the Gibbs free energy Ga will increase from Ga plus dGa. This is the increase in Gibbs free energy for phase A. Similarly, for phase B, the Gibbs free energy will increase to Gb plus dGb. At equilibrium, this Ga, and that we know already, Ga plus dGa, that's Gb plus dGb will be equilibrium, will be equal at equilibrium. And therefore, we have already seen that Ga is equal to Gb in a previous. Okay. And therefore, this equation can be modified like this. And these two become, this will cancel out, Ga and Gb. And now dGa is equal to dGb. Let us consider this as equation 1. From thermodynamics, we know that dg is equal to vdp minus sdt. This is an equation of state in thermodynamics. And therefore, we can modify the equation 1 accordingly. dga is equal to va and dp minus sa into dt. And similarly, dgb is equal to, dgb means changing Gibbs free energy, that is equal to vb dp minus sb dt. And substitute the same in the equation number 1. Substitute these values in equation number 1. I get this value va minus vdp, va minus vdp is a minus sa dt, that's equal to vb dp minus sb dt. Okay. va dp minus vb dp, that we can modify. Okay. I bring vb dp here this side, and therefore it becomes minus. So va dp, both dp I am bringing to one side and dt and other side, the dt component, and therefore va dp minus vb dp, which is brought this side, becomes minus. And similarly sa dt, from here it went to other side, so it becomes positive sa dt minus sb dt here. Okay, or we can also change this equation into vb dp minus va dp. For example, how can I get this equation? Just multiply this equation with minus on both sides. If you multiply and minus on both sides, this will become minus and this will become plus. This is how this equation can be vb minus dp, vb dp minus va dp, that's equal to sb dt minus sa dt. Taking the dp common, we will get a vb minus a va. And similarly, taking the dt common, taking the dp common, we get vb minus va, and taking the dt common, we get dt into sb minus sa. Okay. Now consider the same equation dp by dt. You know this. Now here we have a dp here and dp minus, okay, I'm bringing this dt here, and so that I get dp minus dp divided by dt, that is equal to sb minus, and this is here and this goes this side, and therefore you get sb minus sa divided by vb minus va. Okay. And just that sb minus sa is known as delta s. We can change that into delta s, and vb minus va, I can say it is a delta v, and therefore this equation takes this form. Now, while rising the temperature from T to T plus dt, okay, a Q amount of heat, that the energy is heat, heat is exchanged between, okay, and therefore we know from thermodynamics that delta S is Q by T, irreversible by T, that is from a second law of thermodynamics that we have already known. And substitute this value in the delta S here. Well, on substituting this value, this equation 5 becomes dp by dt, and for delta S I substituted Q and T, Q by T, and then the same delta V. Okay. Or this equation can also be modified like dp by dt by Q by T or Vb minus Va. And this Q, the amount of heat absorbed, can also be equated to the enthalpy change that is taken place in the system, and these are, and therefore I can also modify this equation into delta H by T into Vb minus Va. Okay, And this equation number 6 I have put, and this equation and this and all of these, okay, all of them are same, and this equation is called as a Clapeyron equation. Okay, from this Clapeyron equation, now we shall derive the Clausius Clapeyron equation. Okay, Clausius Clapeyron equation, as I have already told, the Clausius Clapeyron equation is the modification of Clapeyron equation according to the phase transition from liquid to vapor, liquid to vapor phase transition. Let us consider, and therefore a liquid is in equilibrium with the vapor. The Clapeyron equation for this system can be written as dp by dt, that's delta h by delta h, and that I have used already, that I have used here. The process is vaporization, therefore I consider this enthalpy changes, enthalpy of vaporization divided by T into that VB minus VA I consider here vapor and volume of vapor and volume of liquid. Now let us consider an example here, an example of 1 mole of water. Okay, if you consider the volume of vapor will be much greater than the volume of liquid. Let us take, for example, in case of water at 100 degrees Celsius, the volume of vapor will be this much. Yeah, this much, 30060 ml, this much, 30,000, more than 30,000 ml. That is the volume occupied by 1 mole of okay, but the volume of liquid that occupies is just 18 ml. And if you compare VV and VVL, it is the VL becomes negligible. So VL becomes negligible, and therefore the delta V that we have already seen, delta V that we have seen here, this delta V that we have changed into VB minus VA. Know that? Okay, that is here we have changed into VV minus VL, and that becomes, because it becomes negligible, that is 0, and therefore it is approximately equal to volume of the vapor. And substituting this in the equation, I get dp by dt, that's equal to delta H vaporization divided by T into volume of vapor alone. Okay, for, and we know from ideal gas equation, I am substituting the value of V in the ideal, the value of V I am going to substitute using ideal gas equation. Therefore, I took ideal gas equation, that is PV is equal to RT, and from that V is equal to RT by P. Okay, I substitute this value in this equation, I get dP by dt, that's equal to delta H vapor divided by T into, in this place I substitute RT by P, therefore RT will be here and P will go upstairs. Okay, that's what I have given here. P will go to the numerator. Okay, now the dP by P, I am bringing the P here, bringing the P this side, and therefore dP by P, that's equal to delta H vaporization, okay, divided by T into RT. Okay, I multiply this and that becomes RT square. I bring this dt here. Okay, and therefore dP by is equal to delta H RT square into dt. Now, and the dP by P can be written as dP by P can be written as d ln P, and that's equal to delta H by R and dt by T square. I separate this T into here, all of both are same. Okay, and this equation is known as a Clausius Clapeyron equation, d ln P by R into dt by T square, Okay, this equation is known as Clausius-Clapeyron equation. And now we are going to integrate this equation to bring the integrated form of a Clausius-Clapeyron equation. Let us integrate this equation. If we integrate, okay, let us integrate this equation. Okay, let's integrate this equation and we get integrated form of a Clausius-Clapeyron equation that we can see here. We can see here the integration of dlnp from low pressure to high pressure. Okay, integrate similarly the delta h, I consider the change in the volume is negligible during this process, and therefore I make delta h as constant and therefore bring it out of integration as it is a constant. Okay, therefore delta h by r, and then integrating dt by t square as here. Okay, upon integration, now let us integrate this equation. This dlnp, when it is integrated, it becomes lnp. Upon applying upper meniscus minus lower meniscus, I get lnp2 minus lnp1. Okay, that is equal to delta h by r. The same thing here. And here I integrate minus 1 by t square. That what becomes the t square when it goes to the numerator, it becomes t power minus 2 according to integration formula. N power a power n plus 1 divided by n plus 1. According to that formula, t power minus 2 plus 1 divided by minus 2 plus 1. This is what the integral values. Okay, between the limits t1 and t2. Now, according to the formula ln a minus ln b is equal to ln a by b, I put ln p2 by p1, and this is equal to delta h by r that we have already have. And when you modify this, and this becomes minus 1, and that minus is here. Okay, minus 2 plus 1 becomes minus 1, and that minus 1 is here. Here minus 2 plus 1, t power minus 1. T power minus 1 means 1 by t. That I have this whole term becomes minus 1 by t. When you apply upper meniscus minus lower meniscus, you get this 1 by t2. First we apply the upper meniscus. Here it is minus 1 by 2, and therefore I write minus 1 by t2. And in integration there is a minus, upper meniscus minus lower meniscus, and that minus and this minus multiplied, and that changes into plus, and therefore it is 1 by t1, that is lower limit. Okay, it's not meniscus, it is limit. Okay, now therefore this ln p2 by p1, ln p2 by p1, that's equal to, and I took this minus outside, and therefore I put this minus here, minus delta h by r. Since this minus is taken outside, and this will become t1 minus t2. This will become minus and this will become plus when you take the minus outside, and therefore upon cross multiplication, t1 minus t2 you will get, and t1 t2. Okay, and this is the integrated form of Clausius-Clapeyron equation. Okay, sometimes we use this equation for problem solving, sometimes we use this equation depending upon the situation. Let us see the applications of Clausius-Clapeyron equation. And the Clausius-Clapeyron equation can be used to calculate the molar heat of vaporization. You can see the delta H, and this, if it is vaporization, we can consider this as a delta H of vaporization, enthalpy of vaporization. We can calculate this. We shall see with that with an example. Let us see an example of this example problem from which we can find the molar heat of vaporization. Let us consider this problem. Vapor pressure of water at 95 degrees Celsius and 100 degrees Celsius are 634 and 760 mm respectively. And calculate the molar heat of vaporization, and this is the problem that we have now. To answer this problem, let us solve this problem by taking an example. Let us solve this problem. The solution to this problem is this. We take the given data. Data is given, that is temperature T1 is at 95 degrees Celsius. I wrote this 95 degrees Celsius, and we convert that into Kelvin. Okay, that is adding 273 to this 95, we get 368. And another temperature that is given is 100 degrees Celsius, and that is 100 degrees Celsius. We convert that into Kelvin, that is 373 Kelvin. And other information, the pressure are given respectively. That means for 95 degrees Celsius T1, the P1 is 634. For T2 100 degree, the P2 is 760. This is 760, and this is 760 mm. Okay, and this 760 mm of mercury. We will use Clausius Clapeyron equation to solve this. The Clausius Clapeyron equation says ln P2 by P1, ln P2 by P1, that is equal to delta H of vaporization divided by R into T2 minus T1 divided by T1 minus T2. You can see a slight modification in the equation. Earlier we have seen minus delta H by R T1 minus T2. Now I have multiplied this minus here, therefore T2 minus T1. There is a change, and that is a change here. I have removed minus here, that minus came inside, and therefore T2 minus T1. Okay, now substitute the values in the equation. We get, in order to take logarithm, I convert natural logarithm into logarithm, log base 10. For that we usually multiply 2.303 for converting natural logarithm into log base 10. Okay, upon, okay, the P2 value is 760, that we know here, and the P1 is 633, 634, that we know already. We have to find this delta H evaporation. This is what the problem. And R value we know 8.314 joule per Kelvin per mole, and we know the temperature T2 is 373 and T1 is 368, and divided by T1 into T2, and therefore 368 into 363. Okay, and calculating or rearranging this equation, we calculate 760 by, okay, we get this value. Okay, we get divided by 760 divided by 634, and we get this value, and taking log on that value we get this value, and multiplication 2.303, we get 0.182, and this is the value that comes here. And when you minus this, you get 5, and when you multiply, we get 137.264, this value, and we have all of these things here. Now delta H vaporization is here, and therefore I bring all these things to other side to find delta H evaporation, and therefore this is in denominator. When it goes to other side, it will become a numerator. Okay, that I brought. This value is 0.182, and when it goes there, it is multiplied by, and therefore 8.314, and multiplied by this value. Here it is denominator. When it goes to other side, it becomes a numerator, and this numerator comes to the denominator, and this is the value. When you solve this, I get the value, that is delta H vaporization is equal to 41357.5 joule per mole. You can also say 41.357 kilojoule. If you say in kilojoule, and you have to divide by 1000, When you divide by 1000, this can be converted into kilojoule, and this is the kilojoule per mole. That is also another value. You can also calculate the unit exactly. For that purpose only I have used unit here. Actually here Kelvin, okay, here Kelvin, all those comes. You can see here the Kelvin -1 when it goes. Here it is a Kelvin. Okay, here Kelvin when it goes to there, up a Kelvin into Kelvin, here Kelvin into Kelvin, all those things cancels out, and finally the remaining things only joule per mole, and you can see that is, this is how you get the unit here, joule per mole. The second application, we shall see the second application of the Clausius Clapeyron equation, that is the calculation of effect of temperature on vapor pressure. Effect of temperature on vapor pressure is another application. Let us also explain this using a simple problem. Okay, let us take that example. The vapor pressure of water at 100 degrees. This problem is just like the previous problem, in which the delta H vaporization is given, and the T to P2 is asked. Pressure is asked. Effect of temperature on vapor pressure. Okay, now let us see. The vapor pressure at water 100 degrees Celsius 760, like the previous problem. What will be vapor pressure at 95 degrees Celsius? And therefore, what will be the vapor pressure? Now we are asked to calculate vapor pressure. And the heat of vaporization is already given here, is 41.27. Okay, using this value, we are going to calculate P2. For this calculation, let us take the given data in this problem is this. Okay, delta H vaporization is given, that is 41.27 kilojoule per mole, and this kilojoule can be converted into joule when you multiply by 1000, and therefore it is 41,270 joule per mole. Okay, the temperature that is given is 100 degrees Celsius 373. At that particular temperature, the pressure is 760. 760 mm of mercury is the atmospheric pressure. Okay, and when the temperature is reduced to 95 degrees Celsius, what will be the pressure? That's what being asked. Okay, and let us take similarly take the Clausius Clausius Clapeyron equation. Ln P2 by P1 into delta H vaporization R, T2 minus T1 divided by T1 into T2. Substitute the values, substitute the given values in this equation. We get this. Ln P2 is not, this is what we are going to find out. P1 is already given, that is 760 mm, and that I have put here, and delta H vaporization we know 41,270 joule per mole, and this is in gas constant R 8.314 in joule per Kelvin per mole, and this is T2. T2 is 368. Okay, T1 is 373 and T1. Okay, T1 multiplied by T2. Okay, if you solve this equation, we get I'm using the formula like ln A by B, that is ln A minus ln B. Therefore, ln A I get minus ln 60. I took ln. Here you can use the calculator. If you can also directly, if you use a calculator, you can directly get this value if you use natural logarithm. If you are using log, then you have to take log for 760 and multiply that with 2.303, then you will get this value. Okay, and you must be careful on that. Okay, then this is the log value here, and When you minus this value, you get minus 5. Those things are fine. And and multiplication these two, you get 137264. Okay, and solving these values, all these, I get minus 0.1808, and LNP2 is already here, and minus. Okay, and therefore bringing this on the other side, this will become plus, and therefore plus 6.63 and minus that already here 0.1808, and therefore LNP2 is equal to 6.4492. Okay, and therefore taking this anti-log for this, if you take anti-logarithm, in that case also you have to consider, if you are using logarithm log, then means you have to take 10 power ex, and here it is ln p2, and to take anti-logarithm, that means you have to take e power x, that means e power 6.4492 will give this result, and that is the anti-logarithm. If you take anti-logarithm, you get this value, and that means the pressure will be lower, 632.1 mm at 95 degree Celsius. Okay, this is the second application of Clausius Clapeyron equation. Let us see the third application. The third application is effect of pressure on boiling point. We are going to calculate the boiling point. At what pressure? Okay, let us see with an example. Let us take ether boils at 33.5 degrees Celsius at 760 mm. Okay. The question is, at what temperature will it boil at a pressure of 750 mm? Okay, the earlier pressure is 760 mm. If you reduce the pressure to 750 mm, okay, at what temperature it will boil? 33 degrees Celsius at 760 mm. What will be the temperature at 750 mm? And we are going to calculate that using Clausius Clapeyron equation. For that, we need a heat of vaporization value that is given in the problem. The heat of vaporization of ether is 369.86 joules per gram. You have to note here that it is not per mole, it is per gram, and therefore we have to convert that to per mole. Okay, let us solve this problem. First, let us take all the data given. T1 is given, that is 33.5 degrees Celsius. Upon converting to Kelvin, it becomes 306.5 Kelvin. Okay, T2 that we have to find out. Pressure, we know it is 760 mm of mercury, and P2 that we are going to calculate for 750 mm of mercury. The delta H vaporization is given, that is 369.86 joule per gram. That we have to convert to mole. To convert to the mole per gram, we have to multiply that with the molecular weight of ether. Okay, if you multiply this per gram with molecular weight, we will get a joule per mole. Okay, joule per mole, and this is the value 27369.64 joule per mole. Now we have converted joule per gram to joule per mole. Now substitute the values in Clausius Clapeyron equation. The equation is P1 ln P2 by P1 and delta H vaporization by R into 1 by T1. As I have already told you, I have used a different form of Clausius Clapeyron equation, that I can show you that already. I have already told the class there are different forms of Clausian. The same equation we rearrange in different form as and when it is required, and we can use any of the equation for that purpose. Okay, I am using this equation for calculating. Okay, I have already said this is Clausius Clapeyron equation. You can also use this equation or this equation. For this problem, I'm using this equation. Okay, that's what here. Okay, I'll be using this equation to solve this problem. Ln P2 we know that is 750. P1 pressure is 7 P initial pressure is 760, and we have calculated the delta H vaporization, that is here, and joule per mole, and the universal gas constant, that is 8.314 into the joule per Kelvin per mole. Okay, I have used the temperature here. There is 1 by T1. T1 is 3.306.5 Kelvin, and T2 that we are going to find out. Okay, and upon solving this equation, 750 by 760, 750 by 760 dividing and taking natural logarithm, or you can also divide by 750 by 760 and take log and multiply by 2.303, you will get this value. Okay, and upon dividing these values, you get 3292. Okay, and the same it is here. Okay, now upon rearranging this equation, I get this 392. I multiplied by 3292 divided by 306. Okay, and 3292 divided by T2, the same thing. Now you can, on dividing, you get 10.74. 3292 divided by 306.5, get the 10.74 minus the same thing here, 3292 divided by 32 T2. I'm rearranging this equation to get T2. Okay, here T2 is in denomination. Okay, and when rearranging when it goes there, it becomes minus, or this comes here, it becomes plus. Okay, let us consider this comes on the other side, this become plus, that is 10.74 plus 0.0132. Okay, 0132. Okay, upon now when to find out T2 when it goes here, and 32 will be here. On modification, the T2 here is on, and therefore 3292 divided by 10.74 plus. Okay, this will become 10.7532. Okay, about 3292 divided by 10.7532, you will get 306.1 Kelvin. If you convert that, if you minus 273, you will get 33.1. Okay, you will get this value becomes 306.1 Kelvin. That converting it into Celsius scale, it is a 33.1 degrees Celsius. And these are the applications of Clausius Clapeyron equation. We shall meet in another class. Thank you.